Okay, let's just jump right in because today we are confronting one of the absolute most mind-bending mysteries in the entire mathematical universe. Welcome to this explainer. We're going to be exploring numbers so unimaginably massive that they literally break standard computers, yet they're so fundamentally important. They help keep our entire digital world secure. We are talking about the infinite hunt for Mersenne primes. Out of the absolute infinite expanse of all numbers, humanity has only ever discovered exactly 52 of these elusive mathematical anomalies. Just think about that for a second, right? We've been counting for thousands of years, building increasingly powerful machines to crunch numbers day and night, and yet the grand tally stands at a mere 52. And, well, there's a very good reason they're so insanely rare. They grow at a frankly terrifying exponential rate. Recent discoveries in this mathematical hunt boast over 24 million digits. Let me put that into perspective. If you tried to print a number that large, you need thousands and thousands of pages of paper just to display a single figure. These numbers get so incredibly massive, we literally need vast networks of supercomputers just to comprehend and verify them. Part 1. What is a Mersenne prime? Zooming in on the elegant formula. Before we get totally lost in the sheer scale of those millions of digits, a Mersenne prime is actually generated by a rather elegant, deceptively simple little formula. You just take the number 2, raise it to a prime power p, and then subtract 1. That's the whole shebang. 2 to the power of p minus 1. Now, remember, a prime number is simply a number that can only be divided by 1 and itself, so numbers like 2, 3, 5, or 7. For this formula to even have a chance at creating a Mersenne prime, that exponent, p, absolutely must also be a prime number. Now, what's really interesting here is how beautifully simple the early primes are, stepping so gracefully from 3 up to 127. If we plug in the very first prime number, 2, we get 2 squared minus 1, which is 3, prime. Plug in 3, we get 2 cubed minus 1, which is 7, prime again. 5 gives us 31. 7 gives us 127. It really feels like this perfect, unbreakable pattern, doesn't it? Well, mathematics loves to throw us a curveball. The really crucial point here is that p being prime is a strict requirement for the formula, sure, but it is absolutely not a guarantee of a prime outcome. Basically, just because you feed a prime number into the exponent doesn't mean the giant number that pops out the other side will automatically be prime. And this brilliantly illustrates exactly where that pattern breaks down. For example, if we use the very next prime number, 11, the formula yields 2047. Now look, 2047 might look like a prime number to the naked eye, but actually, scratch that. It's 23 times 89. Because it has divisors other than 1 in itself, it's a no-go, not prime. This single exception is a huge deal because it means we can't just generate these numbers automatically. The search is a true hunt, requiring us to check every single massive result one by one. Part 2. The monk behind the math. Mersenne's 17th century network. This plot twist brings us to the man who actually gave these numbers their name. Mersenne acted as a human focal point, like a 17th century epistolary hub for the absolute greatest minds of Europe. Way before the internet, he was writing letters back and forth, connecting geniuses like Descartes, Fermat, and Pascal. In 1644, Mersenne boldly published a list claiming which prime exponents up to 257 would yield Mersenne primes. But, he was human after all. It turns out his famous list actually contained 5 mathematical mistakes. Yeah, he included 2 numbers that weren't primes and completely missed 3 that were. Yet his influence was so massive that these numbers bear his name forever. Understanding these numbers has been this relentless, centuries-long journey. The ancient Greeks actually discovered the first 4. Then we have Mersenne stepping in during the 1600s. Fast forward to 1772, and the legendary Leonhard Euler verified that the exponent 31 created a massive prime. And finally, in 1996, the great internet Mersenne prime search, or GIMPs for short, began, taking this whole hunt right into the digital age. Part 3. The perfect number connection. The ancient puzzle. Speaking of the ancients, early mathematicians were actually hunting for something called perfect numbers. And a perfect number is simply one that equals the sum of its own divisors. Take the number 6, for example. The numbers that divide perfectly into 6 are 1, 2, and 3. If you add 1 plus 2 plus 3 together, you get exactly 6. The next perfect number is 28, then 496, then 8,128. They are these beautiful, incredibly rare mathematical gems. And here is where it all comes together with the Euclid-Euler theorem. There is a strict one-to-one connection linking every single Mersenne prime directly to every even perfect number. It's like they're two sides of the same coin. If you find a Mersenne prime, you can plug it into a secondary formula, and it will instantly generate an even perfect number. So if you find a new Mersenne prime today, you are simultaneously discovering a brand new perfect number. The two concepts are literally mathematically tethered together. Part 4. The computational challenge, pushing human technology. Now, you might be wondering, why does this matter to you and me? Well, finding massive prime numbers isn't just some abstract academic exercise. It's the very foundation of modern RSA cryptography. This is the heavy-duty math that locks and secures our global internet. When you send a secure text message or buy something with a credit card online, the cryptographic backbone protecting your data relies entirely on the fact that multiplying two giant prime numbers together is pretty easy, but reverse engineering that massive result back into its original primes, that is practically impossible for modern computers. To hunt these leviathans today, computers have to execute 3 relentless steps. First, they select a prime exponent. Second, they generate the massive resulting number, which again can have millions of digits. And third, they must run an incredibly intensive verification known as the Lucas-Lemmer primality test. This test is just computationally exhausting. As the numbers get bigger, the time it takes to actually check them skyrockets. This monumental task has literally pushed computer hardware to its absolute limits over the decades. The hunt evolved from vintage IBM mainframes back in the 60s to massive Cray supercomputers in the 80s, to the JIMPS distributed network linking regular everyday PCs together in the 90s. And most recently, in October 2024, the incredibly elusive 52nd Mersenne prime was discovered by leveraging the massive parallel processing power of an NVIDIA A100 GPU. That's right, we're using the exact same cutting-edge chips that power modern AI to chart the absolute furthest edges of mathematics. Part 5. How far can we go? Staring into the infinite. All of this brings us to a really haunting philosophical reality. Despite our exascale supercomputers and brilliant algorithmic testing, mathematics still cannot tell us if these mysterious prime numbers go on forever or if they eventually just stop. It is a completely open problem in number theory. We literally do not know if there is a ceiling to this hunt. Which leaves us staring into the infinite mathematical abyss with one truly captivating question. How far can we actually go in discovering the largest prime numbers in the universe of mathematics? Are there only a few more waiting out there in the digital dark? Or is there an endless ocean of these giant numbers, just waiting for the computers of tomorrow to pull them to the surface? I hope this explainer helped you grasp the incredible scale of this mathematical hunt. Take that thought with you and keep exploring.